I would like to introduce our next speaker, which is Professor Wael El-Dakhakhneh. He is a professor of civil engineering and computational science and engineering at McMaster University. He is the director of Interface, of the Interface Institute for Multi-Hazard Systemic Risk Studies and the Envision Lab, which stands for Interdependent Network Visualization, Simulation, Optimization, Analysis, and Learning Laboratory. So as soon as we set the presentation, I think, Wael, you are ready to get going.
Okay, good morning, good afternoon, and good evening, actually, everyone. I don't know who's where. As Sharif thankfully introduced me, my name is Wael El-Dakhakhneh, and today I'll be presenting some of the PhD of one of my great students. Her name is May Haggag. Her name is there at the bottom, as you can see. And in the institute, we look at different things. We look at, as the name indicates, we look at the systemic risk, which is a way to simulate the cascade effect and the interdependency of different structure systems, and the interdependency between the different sources of hazard, and the interdependency between the hazard and the infrastructure system as well. Again, as you can anticipate, we're looking into mitigating that systemic risk and improving the resilience of our infrastructure systems and cities across different disciplines. And I'm kind of glad that the presentations before me cover different aspects related to social science, structural engineering, hardcore resilience research, and kind of also sad because it doesn't leave me much room to contribute to new things here. So I'll try to be brief. Oops. So today's talk is really summarizing about 3 papers that May and I have been working on lately. One of them is already published, and it talks about, we did kind of a bibliometric, looking at the different type of publications in the area of resilience and systemic risk. What have they been looking at, and how can we make connections between them, and hopefully creating almost like a roadmap for future research for people trying to get into this area. That was phase 1. Phase 2, we started looking into data-driven models. So unlike many of my colleagues who have been focused on a physics-based model, which is very valuable, we try to look at purely data-driven model, and I'll talk, if there is some time at the end of the presentation, I'll try to talk about not only data-driven models, but hybrid models and models that are really physics-driven, but they're still data analytics, essentially. So in phase 2, we looked into almost like trying to come up with a yes or no scenario. Is a certain disaster going to happen in a certain location in a certain time, or no, depending, again, purely data-driven. But we relied on some of our domain experts in this form of hazard to verify our results. Phase 3, which is the most recent paper that May has been working on, it's looking at large databases, extracting some information about the performance of different infrastructure systems, and eventually coming up with a way to, again, predict what is the probability and what is the location and time and the impact level of damage, really, or the level of disaster, mainly, again, so that in the subsequent paper guide decision makers into what kind of resources should they put, where and when, to make sure that such disaster don't happen in the future. So, okay, sometimes it works, sometimes it doesn't work, and I'm not sure why. Oh, it does work. So the phase 1. So this is a paper already published, and we collected a very large amount of publications from the Web of Science, looking at all sorts of work that has been done on resilience. And there is many ways. Once you collect this massive amount of data and you start doing text analytics, I mean, the sky is the limit. You can start classifying or coming down to maybe 30 different topics, 40 different, 100 different topics, and so on. To make things more realistically, we narrowed it down to maybe 9 subgroups, and there are certain measures that you can look into how to narrow down a certain group of words using different techniques. Within this work, within this 9 topics, we identified that from what you can see here, that critical infrastructure system obviously has been dominating this line of research followed by topic D, which is the interdependence, as many of my colleagues here highlighted, and then followed by the main infrastructure system that typically affects societies, which is, as one would expect, related to energy and water, and so on and so forth. The key insight from this paper was basically it identified certain gaps that researchers who are interested to look into a bird's eye view of this research should look into. For instance, there was many issues with resilience quantification. How can we translate this from purely quantitative into operationalizing resilience, oftentimes with numbers, but also quantitatively as well. So using mixed methods to quantify or to evaluate resilience of communities. Interdependence has also been a big issue, and I'm glad Dr. Baroud has touched upon this, especially considering the uncertainty. System modeling techniques, there's so many system modeling techniques, and the way to integrate this into one platform, and I'm guessing Dr. Tawil will also touch on this in his presentation. Time windows, especially when you consider the dynamic interplay between the different infrastructure systems and maybe social systems as well, and also hazard. This is a big area of research that can really warrant significant future research. Of course, the dependency on the response of the infrastructure on the hazard type is also key. Oftentimes people would say, you know what, we're trying to come up with a hazard interdependent resilience. I see this as particularly difficult mainly because of the interaction between the hazard and the subsystems or the infrastructure system quite significantly. So these are some of the findings from this article. It's already published, you can look it up. And many people are using different semantics for resilience, and there is a way somehow to connect it and to come up with a common language for us to start talking the same language. I think one key thing that Dr. Tawil also is trying to emphasize, that maybe computational language is the way to go. And I would agree, and I would also like to add that we also need to agree on semantics, because across different disciplines, there is a very wide range of the semantics and what do they mean and how to quantify them or how to evaluate them. So this paper attempted to highlight certain key things for researchers trying to go into this area for the first time, or to look at what has been done in this system and how to map different concepts from different papers to other papers and to other disciplines as well. The more of a data-driven numerical part that MAI's research is focused on is also looking at climate disaster prediction. I'm not going to dwell so much into the nitty-gritty details of the model. You'll see this in the publications. But in reality, in a nutshell, this model really looks at, of course, it's a data-driven, so we need to come up with the database, or what MAI does, she collects the data from different databases. The model architecture, this is basically a data-driven model trying to, again, answer, is there going to be a disaster or no? So it's a yes or no model. It doesn't give more details than this based on the data we have. And also it tells you where and when is this disaster going to happen. So considering the amount of climate change attribute that we need to deal. So this model essentially utilizes climate change indices from a variety of climate models across the globe that's being developed. And it's trying to attempt coming up with a hypothesis that, is there a way to link all these climate, or a subset of these climate change indices, to actual disasters that happened in any location? And if this is the case, and considering the number of these input variables that we'll have to deal with within climate change indices, they are typically split between precipitation predictors or temperature predictors for any location at any given time. Is there a way to minimize this number of variables in order to come up with a more easy model to understand? And again, this touches upon that sometimes we need people, not sometimes, all the time, we need people who are domain experts as well to make sense of the data, because otherwise you turn into a data scientist or a statistician, and you don't know what kind of data or what kind of variable should you include or you shouldn't include. And then the third step, you would identify, this was a deep learning model that's composed of many layers. You would identify what's the optimum number of layers or the optimum number of neurons to consider within the neural network model. And then the last step would be model verification through disaster prediction. So we selected a case study in Ontario, Canada. Ontario is the largest province in Canada, and it's especially important because this is where I live. So we selected this this province, and we also had lots of flood disaster data recorded in the province of Ontario over the years. So as you can see, among the many climate change indices, we selected the most relevant 16 based on input from domain experts in climate change models, and 11 precipitation indices. And we considered the period between 1950 to 2016. And the way to look at this is, especially considering the type of hazard we are talking about, we were able to split Ontario into 24 watersheds or catchments. For every one of these catchments, we have all this data, the climate indices, and we know what kind of disaster happened when, at one time as well. When we looked at this case study, of course, if you take, we decided that it doesn't make sense to take all 27 indices. So we started saying, you know what, how about we pick only 10? And even when you pick 10, the number of runs to simulate what is the most accurate model, you end up maybe with more than 8 million runs to look at all sorts of disasters in all years, in all locations, considering different combinations of these 10 indices. So it can be, remember, we have 27 indices, and we're trying to pick some combination of 10 out of them that is kind of accurate across the board for all locations for all time of these disasters. We narrowed them depending on the type of error we are getting. We were able to narrow them down to much lower numbers. And eventually, we decided, again, based on input from our domain experts in the area of flood and climate change forecasting, we narrowed it down to a model that can only take 4 indices, if I recall correctly, 4 or 5, I'm guessing 4, in order to be able to predict the kind of disaster, not the kind of disaster, if a disaster would occur or not in which location. Again, depending on future climate models. So this is the validation step and the picking which the number of layers to include in the model. And again, remember, just the yes or no model. It doesn't have more information than this, again, depending on the data we have. And the model was pretty accurate. If I remember correctly, based on that, like we usually would take about 70% of the data and train the model with it and try to validate the model with the rest of the data, say 30% in this case. And the model was about like 90% accurate in this case. Again, it's just yes or no. To take this to the next step, we try to look into something more interesting beside just a yes or no analysis. So this is the structure of the framework. It's a numerical framework, so I'll show you a case study at the end. So this framework uses, again, it's a data-driven model that utilizes data, both text data from previous disasters, and it's split into 3 different phases, as you can see. So the first phase is the input phase. So usually we have an event narrative. We have text information. People would say, you know what, I noticed such and such damage, and this is the extent of the damage or the performance of a certain type of infrastructure. And they would list all sorts of different infrastructure. And they can list houses, the type of houses, the power lines, different hazards, whether it's wind-related, flood-related, or earthquakes, and so on. So once you deal with this type of massive amount of data in such large databases, especially with text information, then text analytics, and that's the reason why I mentioned at the beginning of this presentation, becomes a key tool. So within the event narrative or the disaster narrative, you can extract many information. You can extract the location of the hazard, if this is not already structured, but I mean, more importantly, the extent of damage is the key thing that you can extract from this narrative. So we had the time of when the event or the hazard started, the location, and many other hazard-related attributes. If, like my previous colleagues, you have additional information like the kind of social attributes or the different, which one is, where is the at-risk communities that have been affected by this hazard, then obviously this adds more richness to this kind of analysis. The internal processes, which is the core of this platform, it links climate-induced disasters to what are the systems affected and what is the damage occurred, again, based on the text analytics. And then we try to investigate what is the influence of the different attributes. I mean, if we add or remove certain attributes from this data, does it impact the accuracy or does it impact the performance of the model? We also need to fill the missing data, because oftentimes it's almost like lessons learned from previous earthquakes. Oftentimes there is so many missing data that you need to fill, and there are certain techniques for filling missing data. You don't just like plug a number that you think makes sense. There is numerical techniques that you can try, and it's also validated with domain experts. And then we develop, obviously, as any other predictive model or data-driven model, you develop the model and you evaluate it and you validate it. So let me jump quickly to, well, one thing also that related to interdependence. So one cool tool that we started looking into this narrative is to look into n-gram analysis. So instead of looking for a certain word, you can mix words. So for instance, power line, hurricane, or substation and flood. So you can start looking for this, and you look at the frequency of the occurrence of these kind of events or these kind of text in the event narrative. And this was very useful because with this very large database, it's not that easy to make sense of text information. I'll quickly show you a case study from our analysis. We looked at the whole United States, and we looked at the different types of hazard and the frequency. So we'll pick at on the state of New York. So within the state of New York, power infrastructure has been shown based on the data set we have to be the most affected or the most vulnerable to hazard, and wind-related hazard especially was the key hazard that affected power infrastructure. We were also able to classify the hazard based on the event narrative. So either it's no hazard, which is class 1, component hazard, which is say a power line or a pole, we consider as a component damage. And then we'd look at complete outage. So this is a system-wide outage within a local area. So this is considered the system damage, or it's much like damage state 1 and 2 and 3 if you're talking earthquake engineering language. This is just some exploratory analysis, again, showing you that wind and thunderstorm hazard is the most critical type of hazard for this kind of infrastructure. It also shows you that it's the seasonality effect. I mean, depending on when is this type of hazard occurring and what kind of classes do you expect to happen, whether it's almost no damage or component damage or prevalent system damage. And I think one cool way of showing this, before I jump to this, so this shows you that, for instance, regardless of the magnitude, and I know there is a big variance here, but if you look only at the mean magnitude of the wind, it doesn't really give you much information, because they will all fall class 1 and class 2 and class 3 damage essentially have more or less the same average magnitude. Duration might have a different impact, but again, class 1 is no damage, and you see the variation in duration. So this tells you that whenever you come up with such a complex data, it's not that easy to use traditional statistical analysis techniques, and you really need to use machine learning techniques for this. This is one of the cool outcomes that we were looking at, that if you look at the state of New York, so remember, class 2 is a component damage. Component damage is like a power line failing, or a pole or tower. Class 3 is the system-wide. So pre-2004, there was lots of outages in the state of New York, according to the set we have. Between 2004 and 2003, the system outages were mainly in the western of New York, and the component was in the east And then from 2011 to 2019, I mean, there's lots of component outage, component damage, as you can see, class 2. But mainly the system outages started to concentrate in the east, more to the left. Again, we're not domain experts in this area, and this is where the role of a domain expert would come and say, you know what, maybe, and I'm not sure about this, but maybe there is, they changed something in the system that made it, there's more interdependence that causes more system level outages compared to just component failures. The issue of aging infrastructure, the demand that might have increased. We're not really sure of this at this point, mainly because we need to add more layers to this analysis. I'll skip this, but the way, whenever you have to deal with data, you oftentimes will find there's missing data. And there's many ways of looking at the missing data. One technique we applied here is to use classification, unsupervised learning to cluster the different data. And whenever we find data that's missing for duration or magnitude of a certain hazard, then we usually give it the mean of this particular cluster. So that's one way of looking at it. And it significantly improved the predictive accuracy of our model when we filled the missing data versus not filling the missing data. Another thing that maybe you need to worry about whenever you do like this kind of data-driven analysis is to use stratified models. So if you can't just pick a data set randomly that has to train the model that has mainly significant damage or class 3 or system level damage or only class 2. You usually use stratified, use some of this and some of, I mean, equal amount of all the damages or damage class as much as you can. I think, so one, this just shows the classification tree. So remember, we're dealing with categorical data, which is classes, but you can also use regression tree if you have some numerical data to deal with. One interesting observation is we started trying to eliminate some of the attributes we consider, to say the wind duration. And if you eliminate the wind duration, then the accuracy of the model goes down a bit. And you can see for the different types of attributes that we considered into the analysis to predict the performance or the damage of the infrastructure, it's almost essentially everyone was very relevant, as you can see from this analysis. And I think this was the end of it, Sharif.
Okay, thank you, Wael. Very interesting presentation and a very different angle from most of the other talks that we had today. So this is focused on data and the use of machine learning and artificial intelligence to do some of the things that we do also with the physics-based models. It's very interesting perspective. So there are a couple of questions. One of them is from Omar Siddiq, and he says, thank you, Professor Wael, for your interesting presentation. I have a question about how to use the collected and predicted data as input to computational tools to simulate the interdependencies between the different systems in the community.
So I think Dr. Baroud mentioned this too. So there is a way, for instance, I mean, if you only go data-driven, I mean, obviously depending on the accuracy or the meaning, how meaningful is this data. The data will give you indication of interdependence. So there is many ways of looking at correlation matrices. There is a technique that one of my postdocs came up with, which is synchronizing the data. So if something is really dependent, you can look into a technique called synchronization, and we borrowed this actually from electrical engineering. There is many ways to look into this, but I think the key is, maybe the better question is, can we only look at data-driven models to guide like future climate resilience? And I don't think so. But also in the same time, I don't also think that we can rely only on physics-based models. The reason being is, if we really understand everything, then I don't think a disaster will occur. I mean, if we know how to solve it, then we wouldn't be hit by doing the same mistakes over and over again. I think to integrate data-driven models and physics-based model into coming up with some sort of hybrid models, that's also needed because of the interdisciplinarity of the resilience problem. I think it's the key. But yes, sometimes we don't know that a system is interdependent on another system, but the data proves that they are dependent. And there's many techniques. You can email me or email my student, my Hagag, and we can definitely provide you with lots of answers to this question.
So the next question is from Ahmed Abdelhadi, and he asks, using machine learning approaches requires a lot of data to provide meaningful results. So based
Yeah.
on your interesting research, I have two questions related to that. How do you obtain this data? And how do you use physics-based models to obtain more data? Kind of related
Okay.
to what you were just discussing a
Yeah.
minute.
So maybe I'll start by answering the first question. So how we used it, I think so like Mai and many of my students who are working in data driven, believe it or not, they spend 80% of their time collecting and cleaning the data. So that collection of data and the data wrangling takes quite some time. And the application of the different techniques, once you understand it at the PhD level, believe it or not, is super easy. But to get meaningful data is key. How can you feed this data into a physics-based model? Well, it depends on what you're looking at. So if you're looking for interdependency that you cannot reveal, then some of the links, if I borrow, for instance, the approach of Dr. Baroud. So she showed you a couple of links. These links, it's either like a physics-based link that you know that if you cut down the power from that particular traffic light, I mean, it will shut down. And sometimes that little link can be a data-driven model in its own, depending on what kind of input, and it can be a black box. It doesn't even have to be a glass box. So it's a black box data-driven model that tells you when you have these kind of input parameters, this is the output you should expect. And these are the kind of cool things that you can implement data-driven model within a physics-based, bigger physics-based model, mainly because you don't know the impact of this particular component.
So another part of the question is how much data is considered enough to provide meaningful results? So you said 80% of their time is on data, but is that enough?
I think this is a general question for anybody working in this area, Sharif. So like, honestly, the sky is enough. The more data, and I keep telling this to everybody, the more data, but not only the more data, the richer the data, the more complex the data, two things will happen. With advanced data-driven models, we will be able to uncover interdependence or connections between things that typically domain experts may or may not consider because it's so complex to the human mind to consider all these aspects. And this is where the domain expert role would come into interpreting the data. So if you see something that doesn't make sense, this particular attribute always affects something, a certain phenomena. There is a reason for this, but as someone who's just like a statistician or just handling the data, they don't really make sense of that. So I would say the more data, the better, and the more complex, the better. But again, we will just work with whatever we have. So in our second phase of analysis, we're just coming up with yes or no analysis because we didn't have more than this. Once we got much richer data, we were able to classify the different damages. And again, based on text, there was no numerical values there. And we came up with a more, I would say, a bit more meaningful analysis of what to expect, especially with resilience. If you are talking about the damage and the cost and the time it will take to recover. If we have better set of data that includes social aspects as well, then we can really quantify different things.
In just 1 minute, the very last question, so that we can switch to the last speaker, is what were the semantic related challenges that you encountered?
I don't think we came up with lots of challenges there. The challenge was just to collect the data and to either decide whether to look at, for instance, the title of the paper or the abstract of the paper, which is many people would do, or to go in depth inside the paper text itself. We decided to go into the abstracts mainly because we knew what topic we are talking about, and typically the abstract you would hope that it would cover the extent of what's in the paper. In R, which is the software or the language that most of my students are using, there is many libraries already built in that can handle this. So it's not something that you would need to program from scratch. There is many existing libraries, and as long as you know what does it mean and you know the tokenism and the many steps that involves text analytics, I think it's pretty straightforward.
Okay, thank you very much.
Yeah.
I appreciate you coming to present today and providing your unique viewpoint.